Right, I decided to make another video because I wanted to explain a little bit more about these safety boards. Now, originally I was doing some tests actually. Now, I actually put some capacitors across where the batteries normally connect. Now, just to explain it, I'm going to get this other board because it's a little bit easy to see the writing on it. But on the board, when you take them out of the battery packs, you'll find out that there's some connections called VM, VH and VSEN. Now VH means volts high and volts medium. Basically what that means is that the volts medium is connected to the first cell, so the cell's connected to ground, and the B sense, that's the negative wire. B sense actually goes to ground. So volts medium, the yellow one, on this particular one is yellow because they're different colours on different packs, but volts medium actually goes to the first positive terminal of the first cell, which is 3.7 volt, right? And then volts high, VH, volts high, actually goes to the second cell, which is 6 point, let me see, I think that's 7 point, I can't remember now, I'm getting confused, but it's the second cell, two 3.7 cells or 3.6 volt cells in series, so that goes to the second cell, volts high, and this is for a 3 cell pack, you know, either a 6 cell with paired up into twos, so the actual wiring is that the volts medium goes to the first cell, volts high goes to the second cell, and obviously the positive of the 11.1 volt voltage pack is takes the sense off the main supply anyway. So but anyway, I just thought I'd explain that because the problem with these safety boards is that once you disconnect them from the power from the battery, most of the programming is lost. Now, I've discovered that there's actually a data input on the socket, and I don't know if I can see on here, but you can actually see there's P minus, which is ground, P plus, which is positive, and then there's a D, and then there's a C, and then there's, actually I can't see it properly. Now I think the D is for data. Now I understand that you can reprogram these boards using a serial connection. The trouble is every single one's different, so there's no point me trying to explain it. But what you do is you find the main EEPROM chip, the main chip that stores the, I think this one actually comes apart, just a minute, let's see. Some of them actually got plugs on. I'm not sure if this one has. Some of them you can pull them apart. This one's stuck together. I think it's soldered, this one. But some of them you can pull apart. But there's a chip on them that stores the EEPROM stores the programming, and you've got to look up the actual EEPROM or the actual chip that controls the circuit. I took this out of an 11.1 volt pack, that's why I wrote down 11.1 on there, so I could remember easy. But now you can actually find out on these how to reprogram them yourself using serial data connections, but obviously not all. Some of them have default settings, and some of them just revert to the default settings, which is probably more suitable for me anyway, because of the fact that my battery pack probably far exceeds what the board's capable of measuring anyway. But I was just thought I'd do this update, but they're all basically the same. This board here, this is another one. I think it's upside down. Right. That's got a terminal there. that it's got volts. It's a bit smaller, volts high, where you connect a wire for the first cell, and then there's another connection there which is covered up in this gunk, because I just pull these out of the old packs, but just clean this connection up. It's thermal paste that they put on there. Let's see if I can get this off. I managed to put an extension lead on here. Right. I'll just see if I can read that with my magnifying glass. That looks like ground, that end, yes, because and there's another temperature coupling thermistor on the end there. And anyway, they're all basically the same, except for the chips and how they're programmed. What I did was on another one, I got the number off the microchip and searched online, but on some of these you can't read the writing. But from what I can see, this one, it's hard to read it, but the writing is usually faded anyway. But I did actually pull up a particular one which I found useful. I'm just going to open this file which I saved and have a look. There's a website called www.ti.com product actually www.ti.com/product/BQ2040 /tools software. And anyway, one of them is an EV2200, and there's an EV2200-40 programming kit, interface board and software and cable for an IBM compatible PC is available for benchmark. Now apparently that particular one is easy to program, and you can configure the temperatures and voltages and everything. As I say, I've got a few of these, and this one's covered up in a lot of gunk actually, but it's the same. If you look at the end, there's it's upside down, sorry, but it's the same there. Volts medium, there's a thermistor on there, and there's volts low, VL, just here, volts low, VL, BP volts positive, that's connected to the red wire here. And if you take these out of the old lithium ion battery packs, you can often, what you find out, now I'm just going to get my little needle, my little pin. What I've got to find out is which connections on here are positive and negative, because the board actually controls the output and charge current. You'll usually find that the negative is at one end and the positive is at the other end, completely opposite, and the data pins are in between. So the way to find that out is to get the multimeter and connect between, on this one the ground wire is clearly black and marked there, so you connect a multimeter between the ground and then the pins on here to find out which is ground. And once you find the ground, sometimes the ground is switched though, so you've got to do the same test for the positive to find out which one of these is positive, because the microchip inside there controls the output if the battery voltage drops below 3 volt per cell or on one of the cells, then it will switch the voltage off, so that the battery is no longer discharged. Now the way it works normally is as soon as the voltage is applied to the input pins, it will reactivate the circuit, as long as the circuit's not completely redundant, as it's lost all its programming details. Some of these boards, you can recover them simply by applying the correct polarity voltage to the positive and negative terminals, and then you can use the board for at least the basics of controlling when the power is on and off, and depending on how charged the battery is. I'm just going to stop this a minute. Right, okay, I've got my meter here. Now, as I say, if I connect this black crocodile lead to the negative terminal on this board, and I connect the other end to my meter, the negative terminal on my meter. Now I'm going to see which one of these pins is ground on here. Right, that's ground. Right, the rest of them will not give a reading, but that one does. So I've determined that this end is ground. Right, so this board is always ground at one end. So basically, and then I would I'll switch my wire to the positive, test to see if there's a positive, and there's not on the other end. So on this particular board, positive is switched on and off by the control chip, and I would most likely presume that positive will be the opposite end, because that's the way they do it on these boards. I've checked loads of them, and it's always the case that negatives at one end and positives at the far end, the other end of the board. So if I connect this board to some batteries using my crocodile clips, I should be able to activate the board. And the way to normally do that is to do a feedback loop from the positive terminal of the battery to the positive terminal on this board here, which is the output. And normally that would be initiated by a charge voltage, you know, negative and positive coming in to the board, and that would normally initiate the pack and enable this to supply voltage out. So I'll have to hook this up and see whether or not we can do that. I'm just going to have to pause a minute while we do that. Right, okay, I've got this board wired up now, and normally what you would do is to trigger the board is apply power. Now I've got this wired up to a limited power supply which runs my light, so when I connect this you'll see my light dim. The reason for this is this particular battery is very flat, which is why I wanted to use this pack, because it's actually quite flat. It wants charging. So what happens when I connect the positive and negative? Let me just get the camera a bit nearer. Sorry about the focus, it's because I set it up so that it would work. I suppose I better adjust the focus on it now actually. Right, that should be a bit better. I'll bring this a bit nearer if I can. It's not going to be very easy to do this because... Right, I've put a flashing LED in the positive and negative terminals of the battery pack. Now, when I apply a voltage to the LED, the light will dim because the power is going into the battery pack to charge the battery pack. Now you'll see the LED flashing. Now when I take this away, normally if the pack was charged, the LED would stay on. But because this pack has a low voltage, the LED well, it's a flashing LED, so it doesn't need a biasing resistor, by the way, it's built in. Just to prove that, I will take the LED out of the socket. Now I'm just going to apply the voltage directly to the LED now. And now you'll see the LEDs flashing. And it's hardly using any current at all. That's because the LED is not taking all the current when I apply it to the safety board. So I'll plug this back in. It's a bit fiddly because these sockets are designed for laptop connection. Now if I apply the power again, oh, it's not connected right to the pack. That should be it. There we go. Right. So the pack is taking most of the current, and the LED will not stay on because the pack needs charging. Now, what I need to do now is stop the video and try to get enough power into these battery packs so that the LED will stay on. And the reason I'm making this video, actually, I needed to mention, is because I did a search on YouTube regarding safety boards on lithium ion battery packs, and I couldn't hardly find any information on them whatsoever. It seems to be either a well-guarded secret, or people just haven't bothered to take the time to study them. So I thought, well, I'll make a video because I have been studying them. And I'm probably in a unique situation, really, because I mean, not everybody has about 100 lithium-ion battery packs to take apart, and there's such a variety. There's so many different types. Now, I'm not exactly digital whiz regarding how to program these, so I'm sure somebody out there could actually look into that a little bit more. My main objective really is to find the ones which work, because I don't want to be messing about too much, because most of them are configured and have a maximum of 10 amps or something, from what I understand. So they wouldn't, even if I was able to program them, there wouldn't be a lot of use as regards programming them on current limitations, because my battery pack which I built far exceeds the 10 amps anyway. So I'm basically just using them as for thermal monitoring, using the temperature sensors, and also to protect the battery from being fully discharged, which the board seemed to do anyway without programming. So that's satisfactory. So anyway, I am going to attempt to charge this, and I can't really charge this with this 100 milliamp job here. So what I'm going to have to do is get my LiPro charger and boost some charge into them that way. Right, using the LiPro balance charger. Sorry, I can't get it in full shot here. I'll try. It's the camera's at a funny angle. LiPo balance charger. Now I'm going to hook this up, and I'm going to connect it directly to the LiPo. Can't charge these cells up through this board because it has to have direct battery connection. So I'm going to have to cheat a little bit. I'm going to wire this up onto these terminals. It's a bit hard to see what I'm doing here. Very fiddly. Actually, I should better connect directly to that clip there. Oh, I better not do that, because I'm going to pull my little board all over the place. Get onto the battery direct if I can. And I want these wires are a bit fiddly. It's a homebrew sort of balance lead, crocodile clips. Right, get this next one on, and then the positive one on the end. Now I need to get the main lead. Such a lot of wires all over the place. Negative. I'll try and put this so it's out of the way. I don't want to block the camera, do I? Right. Now let's turn on the LiPo. If I can find the hole. Okay, that's that turned on. Right, now I have to set the let's see if I can move the camera a bit. Now I have to set this to LiPo balance charge. So I want that's right, LiPo balance. Let's see, set it to 400 milliamps, and it's 10.8 volt cells, 3S. Start. Doing a battery check. Confirm. Okay. Right, I'm putting some juice in now. It's the light's reflecting off there. Right, hopefully we can bring these cells up to a reasonable amount so I can reactivate this and show you that this board does actually work. Now, I'm not interested in what the charger's saying right now, but I can relay the information. Now, the important thing is the fact that these boards, these safety boards, now when there's enough power in this cell, in this battery cell, when I apply a positive voltage to the output pin of the safety board, that LED should stay on. Well, it's a flashing LED, so it will flash on and off. Now let's just try it, because it's actually being biased heavily up to 10.5 volts right now. So it might actually stay on once I trigger it. Let's just try this. No, not yet. No. So the battery clearly needs more juice yet. So we have to continue charging until the cells are sufficiently charged for this board, this safety board, to keep the output turned on. And just to validate that this is correct, put my meter again on continuity. This is the negative probe, this is ground. Yeah, that is ground. That's wired correctly. I've actually stuck one of the wires into the socket with the LED. So when this is charged up sufficiently, hopefully, provided this board isn't faulty, and some of them are, because as I say, I took them out of bad battery packs. Now the battery packs were either faulty because of batteries being dodgy, or they were faulty because of the safety boards failing for whatever reason. However, the fuse on this safety board has not blown, so, and the fact is, when I apply power here, it does actually charge the cells, which is the reason for it drawing all that current. So, but it's not actually supplying current out yet. Now, another way of doing this is to, I'll get my roll of solder because I'm a bit short of bits of wire. Another way to do this is to take power from the positive terminal of the battery. This is my solder, I'll use a bit of that, which is this red wire here. Take the positive terminal of the battery and touch the positive terminal of the LED, and it's not staying on, so obviously the batteries need more charging yet. But anyway, we'll come back in a while and see how it does, how it's doing. At the moment we're only at 10.21 volts. Actually this LiPo charger is dodgy anyway, because it's actually reading, it's reading about a volt out. So when it says 10.24, it's actually more like 9.24. This is, I actually complained on eBay about this one because it wasn't accurate. I'm talking about the LiPo, this thing here. It's actually a bit out of calibration, so I use this very sparingly with extreme caution. Another reason to be careful with these things is because if you overcharge LiPo lithium ion batteries, you can cause fire or explosion, so you should be very careful. So just a better view of the way I've got the balanced charger, a LiPo charger, connected to all the cells. Well, it looks like spaghetti junction, I know, but it's on the management board. Volts low is the first group of cells, first pair or first single cell. Volts high is the second cell, one cell down actually from positive, and obviously volts really high is the total voltage of the pack, and that's usually carried by the main positive terminal anyway. And they usually only have, on a 3S pack, you normally only have 2 sense wires, well actually 3 sense wires. There's a black which goes to ground, negative terminal of the battery. It actually senses current, supposedly. So, well, we're still actually charging, and let's see if there's anything yet. Nope, the LED doesn't stay on, so the battery still doesn't appear to have enough power in it yet. So, see, these circuits vary. Some of them actually can be reactivated as soon as the cells are above 3 volts per cell. And on this particular one at the moment, the LiPo charger is telling me that the first cell is 3.53, the second cell is 3.51, the third cell is 3.52. So it's see, it's hard to move the camera around. So it's not exactly get this right. It's not exactly God, the camera's going to fall off now. I had to balance this on something to hold it up, but I don't know if you can see that. Well, anyway, that's the cell voltage is. My camera's going to fall off in a minute, so that's it. I've got it re-anchored. Okay, tilt this back down again. We'll come back as soon as we can get enough power in this thing. Well, I destroyed this board. I attempted to put the positive charge lead directly onto the positive charge input of the board, and these safety boards are very sensitive, so I thought I'd mention it because then you won't do it the same thing. Don't apply a LiPo charger directly to the positive terminal of the charge board, because it destroyed it, and basically I'll show you what I mean. It no longer takes any current to charge the battery. That's why the light is no longer dimming. So I'm going to put this other board on, which I've got, as I say, I've got tons of these things, so I'm going to try it with another board, and Obviously, if there's a weakness like that, I don't want to be fitting something like that into my battery pack that's going to fail so easily anyway. So I'm going to, I've just been testing the connections on this little board, and the yellow on here is, let's see, volts medium, and it's actually a black wire, but it's got a white sleeve. There's actually it's a white wire with a black sleeve, so that's volts high. So you've got to be careful to get these things right. It's actually not black really. I can get it on. It's actually got a white wire underneath the sleeving, so that's volts high. So I'm going to have to disconnect this one, take this LED out, because it's take the negative out, disconnect the negative terminal, disconnect that one, that's positive. Hopefully I can do this without too much farting about. Actually, I've already got some wires soldered to this one. I'm not even sure if this one's any good either. I just need to strip one of the wires off. Sometimes you strip the wires and I get a piece of wire under my nail, and that's very painful. So let me just get this positioned on here. Try to do it without. That's negative. That one's negative, so connect that one. Temperature of things in the way. Volts high is over there, so these ones wants to shift around a bit. Volts medium is this yellow wire. Volts high is the white wire with a black sleeve. And this one here, this red one, is positive, so I have to reconnect this one. This purple wire to that one. No sparks flying yet, so right now, with a bit of luck, we should have. I've already checked the terminals on here. Positives at that end, negatives at that end. So let's just see if we've actually got any power coming out of this board. Have I got this right? Let's just check it on my other thing. Let's make sure I've got the Y polarity right. Yeah, that's positive, that end. I connect this to the negative, that's the positive terminal. Now let's see whether or not we can activate this board. We need to connect the negative terminal from my lamp like we did before. I need to take this out again, sorry. Put the wire in first and stick the LED because it's rigid wire and it will help hold that one in. Now get the LED in securely. Now let's see if this can be activated. It's not connected right properly. No, this one's not activating either. So let me put the charge back on. I'll turn the charge off temporarily while I just testing things are right. Let's see if we can activate the board again. No, this one doesn't either. Let's just give it some time and see if this one can come to life. Actually, this board could be faulty as well. This might be damaged as well. So I'll have to dig another one out if that's the case. But I have got a working one over there, which I don't want to play around with because I know it's a good board and it's been working quite well. Over there, you can't see way off camera actually. I've been testing it for a few days now. The reason I decided to use that one from my battery box for the charge circuit is because it comes out of a 8 amp hour pack, which means it's got a much heavier, bigger diode in there for charging as well, which is perfect really for charging such a big pack as what I've got. So yeah, I think it's an 8400 milliamp hour pack it came out of. So these are out of smaller packs, so these will do for experimenting and tests and things. Okay, right, I did actually get this wired up the wrong way around. Now my LED is on the board now. I'm just going to get a close-up of this. Just a minute, let's get this a bit nearer if I can. It's a bit fiddly. Right, now the LED is connected to the, actually this appears to be positive at this end, but it's not, because the circuit on the other side runs around and it's positive at the other end. Now what we have to do is trigger the board. Now the circuit is charging up the battery. Now with these boards, the board will not produce power until the circuit is triggered, and the way we do that is applying a short duration of positive energy into the positive and negative terminals of the battery output. Now these wires are connected to my lamp. All I have to do is briefly connect positive and negative. Oh, wrong way. It's alright, that's why it's 100, that's why it's current limited. Right, there you go. Now this board is active now. The board is supplying power on its own to the LED. Now there's actually a little bit of a bad connection on the LED because it's those sliding connections. Now these batteries are charging up. Now what happens when the cells are discharged to a certain point is that the board cuts the power off to the output, preserving the cells, protecting the individual cells. So when the voltage on the cells drops to 3 volts per cell, this board will cut the power off and preserve the battery. Because lithium ion cells, if you discharge the cells too much, you'll destroy them. They will deteriorate and start to corrode and do what batteries usually do, which is basically decompose. So the safety board is very useful because it protects your battery from being too discharged, too fully discharged. My camera's going to fall off in a minute. Just a minute. Move this back a bit. Right. Now I have stopped the charging of the cells, the battery. Now let's go into discharge with my Live Pro. Oh, I can't get this in now. Sorry, I don't have a wide angle lens on this thing, so it's a bit fiddly. Now if I go into discharge mode, let's charge. Now if I go into discharge mode, let's see, 9 volt. Let's set this to half an amp. There's not a lot of power in there. Oops, wrong one. Because I'm doing it on here and it's discharge. Where's discharge from? Right. Press start. Right, we're discharging now. Now, when that battery gets down to 3 volts per cell, the LED will stop flashing. The circuit board, the safety board. Just get it lined up. the safety board should automatically cut the power off to the LED. And as I say, if you can find any old lithium ion battery packs on laptops, and provided that the safety board inside is okay, you should be able to use one of these boards to run a MOSFET, a power MOSFET. And the way that would be done is that you would take whichever switched output, whether it's positive switched output or negative switched output. Obviously, if it was a negative switched output, you would need to drive a PNP transistor to drive a power MOSFET to drive the main load. But on this one, this particular board, the ground connection is always connected to ground. So on this one, it's the positive, which is actually at this end, because on this one it's the positive terminals here. So we would actually be able to use the positive output of this board to drive a 1 mega ohm. A 1 mega ohm resistor is actually adequate to drive the gate of a power MOSFET. One of the power MOSFETs that I would suggest using, let me just find it, because I've just ordered another one actually. They're very cheap. I'll just get you the number. Right. It's an if you go on eBay, it's an IRF. That's India Romeo Foxtrot 2807N channel fast switching HEXFET power MOSFET. And actually on eBay you can get them for about £1.78. I think that's about $3. Get one of those, and I believe they're rated at about 80 amps. Just clamp one of those things to a large piece of metal, a heatsink, and then you should be able to drive quite a good load on that. And so instead of actually putting a lot of stress on these little boards, which are only designed to, I think, supply a laptop with about 3 amps, you could quite easily run a power MOSFET and deliver much more than that. Obviously the way it would work is the power MOSFET would be, I think the drain goes to ground and I think the source goes to your load. So you would actually be switching the gate on, and then the MOSFET would actually be switching your negative supply on and off. So your positive on your battery, your positive terminal on your battery would be on all the time, but you would be switching ground on and off. That is the way it would work. So it's a bit confusing, I know, because obviously using the power output, the positive output of the board on these safety boards to switch the power MOSFET on and off, but you're actually switching the ground. So you would be using the MOSFET for ground switching, neutral, negative terminal. So anyway, that would be useful, and also you'll be taking advantage of some of these safety boards which already have thermal coupling. Now there's a thermal coupling thing here. Look, this little thing here. Now I haven't actually tested this one. Let's just find out whether or not it reacts with heat. So I'm going to light my candle. Right, I'm going to light my candle. I don't want to melt anything. I'm going to put my steel, it's a steel rule actually, it's metal. I'll put my steel ruler on top of the candle, and now just, if you hear a loud scream or anything like that, then it's because I picked up my steel ruler without cooling it down. And oops, it's not hot yet, but I'm going to attempt to, I don't want to melt the thermistor. I'm going to attempt to rest one of the thermistor on my steel rule. And I'm hoping that it turns that light out, that LED off. I actually can't even see it on camera. Let me just move my camera a bit. And my ruler's getting pretty hot now. I'm going to rest the temperature sensor on the ruler, and I'm hoping that it cuts the power off to the LED. Obviously I don't want to melt anything. You've probably seen smoke rising up now. Of course, getting good thermal conductivity. Oh, I pulled the wire off my safety board. It's the volts medium, and it cut the power off. That proves that that works. So one of the cells went dead then, according to the board. Just a moment. Now I have to move this without burning myself. I've got to re-trigger this board, this LED. There we go. I just re-triggered that. Actually, I'll tell you what might work. Some thermal service or heatsink silicon compound paste. I'm going to put a little dab of it at one end of my ruler, because I am not getting I'm not really getting heat transfer to that thermocouple, and I really do need to test if these temperature sensors are working, and without touching my ruler I'm going to slide it along with my rubber. Now if I just gently rest this again in my, without pulling the wires off the battery sensor again, I'll gently move these wires out of the way as well, and I'm hoping that this senses a high temperature and cuts the power off. But you see, the board might not actually, might have lost its programming, so it might not know what temperature, it might not be set, so it might not do anything. I'm just resting my thermocouple on there. These things take time. My ruler is very hot right now, probably very black underneath. Well, it doesn't appear like this board is going to react to temperature. It's not turning the juice off. Maybe it needs both of them. There's actually two temperature probes on this board. And yes, this is a steel ruler, so the heat will transfer all the way along the ruler, so it will should be hot enough at that end. And I'm not going to pick it up and find out. So obviously, if this doesn't cut off based on temperature, then I will have to build my own. I'll have to use my own or use another board which does. Now I just need to get this steel ruler out of the way because I'm going to use my pliers. Use my steel pliers to pick this ruler up because it's very hot right now. And I'm going to move this over here and just see whether or not we get any action over here. Because that's a very hot point there. And it's not triggered it. Oh, yes it has. Yes, it has just shut the LED off. So it does work. That is, oh, and look at that, it's come back on again. So I am very happy. I am very happy that this test has worked. I put the steel ruler, the hot part, next to the temperature probe, and it cut the power off. Let's just try that again without burning myself. Yeah, there you go. It cut the power off. The heat from the ruler. Now it should come back on in a minute. Let's just wait. Keep this still. There we go. It's come back on again. So you can find a safety board that's thermally protected. And I'll suggest you do the same test that I'm doing. Get a steel ruler, get it nice and hot, wire it up, test it, make sure the safety board is working before you put this in your own battery pack. Now I'm just going to get rid of the steel ruler now, put it on a steel set on a fire hearth, well, electric fire, gas fire thing. I'm just going to stick it in the gas fire where it can cool there. Move my candle out of the way and put this back down here. Okay, I have got thermal protection with this board, and it's got two probes on it. There's one over here and there's actually one over behind the LED. You can't really see it there, but it's this one here. Right. So there's two of those, and I've got some more probes actually which have got longer wires on, so I can probably just substitute the ones with the long wires. And so I'm happy about this, and saves me having to build one from scratch, so it cuts out when the temperature is very high, which is good. And can't find my tweezers. Oh, there they are. I'm just going to put this candle out. The way I do it is usually get my tweezers. I'm just doesn't make as much of a smell when you do it like that. And so this also now, when the battery gets discharged, and at the moment the cells are 3.48 volts, and one cell's 3.47 volts. So we've got a little ways to go yet. So I don't know if I can get this on camera. There we go. Right, so we've got a ways to discharge this yet, and damn thing's bloody hot as well, which is another thing. This particular one doesn't have a fan in it, and I'm discharging at about 1/2 amp. It looks better when the light's not so bright on it. Right, so when that gets down to about 3 volts, one of the cells gets to 3 volts, then this circuit should cut the power off and protect the battery. So I'll pause right now, and what I'll probably have to do is as soon as it gets close to 3 volts, I'll try and start recording again and show you what happens. Right, what I'm going to try to do is get the LiPo's balance charger in the video shot along with the board so that we can monitor both at the same time. I think I've managed to wedge it up here with some boxes and things to try to get it on screen. So we're actually very close. One cell's at 3.14, the other cell's at 3.12, and one cell's at 3.15. They're actually alternating. I'm still discharging them at about half an amp, and I have noticed that the LED has basically, even though it's a flashing LED, it has blinked or glitched on me a couple of times. I assume that that's because I'm not actually taking a load through the circuit board, and the processor, the intelligent processor on the board, is trying to work out where the power is going, and it's a bit confused because I'm actually drawing the current directly from the battery. The intelligent processor is wondering whether or not there's a fault with the board and that the power has been drained somewhere else. So periodically it's interrupting the power supply to the LED, and then it carries on flashing again, restoring power, because it thinks, oh well, there's no short there, so where's the power going? This board is these intelligent battery monitoring circuits are very intelligent. Actually, they're quite smart. It's obviously trying to figure out, well, where's the power going? Actually, we've got one cell at 3 volts now. The middle cell's at 3 volts, so this should shut off any moment. Any moment now. The circuit should say, right, that's it, the cell voltage is too low, we're going to shut the power off. So let's see if this happens. Actually, the first cell's at 3 volt, second cell's at 2.99, third cell's at 3 volt. But actually, I think they actually cut the power off when it gets down to 2.5 volts per cell actually. But we're very close now, so I'm just going to leave the recording going, and we should actually capture that moment when the circuit says, ah, that's enough, time to turn the power off. And first cell's 2.99, it's oscillating between 2.99 and 3 volt, and the actually they're all pretty well balanced. Actually, this package is pretty well balanced. The LiPo balance charger anyway also is designed to cut the power off when the voltage is below 3 volts, so I'm not sure which is going to go first. If the LiPo balance charger stops discharging the cells before the LED goes out, then I'm going to have to put a load. It stopped. I'm going to have to put a load on this actual circuit board to drain more power until we can see that LED go out. And this particular LiPo balance charger should still continue monitoring the voltage anyway. I know that some of them they seem to record the last. Some of these chargers seem to record the last voltage at the point where they shut down, but this one seems to continue monitoring the voltages on all the cells. So what I'm going to need to do is, actually I know what I can do. I could connect my light, this light here, to the output of these cells, but to do that I'm going to have to go and find some wires, some more clips, and I haven't got any handy, so you're going to have to excuse me while I go and, oh yes, hang on a minute, just a minute, I've just remembered something. Yes, I use these wires which I've been using earlier. Just remembered. Right, so if I turn my light out, I can't see a damn thing now. Connect that one to the battery, negative. connect. Oops, it doesn't want to stay on that wire for some reason. I hate them rigid wires, they're a bit of a pain sometimes. I'll wrap the negative around there and the positive around the positive, and I should get light again. There we go, it's not as bright as it was. Right, now the light, the LED light, oops, it's come off. LED light is running directly off the battery now, this battery that we're testing. Oops, that's come off again. Right, so now when this circuit cuts the power off, when the circuit actually cuts the power off, it will not only turn the LED off, it will even turn the lighting off that you're actually watching the video with. So let me just move this a bit better, and the light will get dimmer. So when the power is a certain point, because they've actually gone back up again on, according to this LiPo, the voltage is 3.12, 3.09, 3.15 respectively across the cells. So actually, to save video, I'm just going to have to stop the video again, and I'm going to have to hope that I catch it the moment when the battery circuit cuts the power off, because it's going to be a while yet. So I'm going to wait until it gets down to, one of the cells gets down to 2.5 volts, because I believe that's what these are programmed for, to cut the voltage off when one of the cells gets close to 2.5 volts. So I'll start recording as soon as we get close to one of those. Right, well, this does appear to be taking quite a long time actually. So what I've done is I've got my electric grill, and the trouble is the LED light, this bright one, has gone so dim now that I've had to put a different light on because it's very dark. So what I'm going to do now is I'm going to connect my drill just temporarily, and it should bring the voltage down. I'm going to run the drill directly off this circuit board, and it should bring the voltage down to the point when the circuit cuts the power off. So I'm just going to hook the negative onto here, and then I'm going to momentarily hold the positive on, and I can stall the drill, and the drill should, in theory, bring the voltage down sufficiently for the circuit to cut the power off. And that probably will happen when one of these cell voltages drops to 2.5 volts, so it might even happen as soon as I connect it. Actually, let's just see. No, it hasn't. So I'm going to connect it again. And this time I'm going to put some load on my drill with my finger. I just want to get the cell voltages low enough for the circuit to cut the power off. Ah, it is. There you go. Oh, look at that. It cut the power off, back on, off, on. The circuit board is doing this. That's because one of the cells is actually, yeah, there we go. The circuit cut the power off, brought the power back on, cut the power off. There you go. There's a reason why on the LiPo balance charger, if the voltage on one of the cells drops below 2.50, it actually reads 0.00. The reason for that is the LiPo balance charger doesn't actually read LiPo battery voltages below that point. So, and it has taken the power off. The drill is still connected, and it has not turned it back on again, which is what we want. So it is actually protecting the circuit. So if I disconnect my drill now from these wires, let's get some more light on, because it's hard to see. Just going to disconnect this and put my light back on. There we go, we can see what we're doing now. Right. Now that the circuit has taken the power off, it can be, as soon as somebody comes along to charge the cells through this board, then if I connect this again, now I've got the light on, connect this to the board through here, it should dim my light. There you go, because it's charging the circuit through that board. Take it off. Actually, it stays on now because there's sufficient power in there to run the just to run the LED. But if I was to put my drill on, it would bring it right down again, and the LED would just go off again, and so the circuit is reactivated. It went off then, right? So it's coming on and off. The circuit is testing, and it goes off again and back on. So that circuit does work. It works quite well actually. It's intermittently taking the power off. I assume that's just to give a warning that it's about to go off for good, unless the cells are charged. So that circuit works great. So it does thermal monitoring, and it's doing voltage monitoring of the cells. So if the cells drop below 2.5 volt per cell, or on one of the cells, then it will turn the power off until it's recharged. So that works quite well. And according to LiPo balanced charge at the moment, I've got 2.83 volts on the first cell, 2.68 on the second cell, and 3.04 on the third cell. So there's a bit of imbalance there, which I expect on these, because these are they're not very new, these cells. But that's not a great difference actually, considering that they're all pretty discharged. So I think that concludes my video actually. It's a bit long, I know, but as I say, I went on YouTube and I couldn't find any information on these safety boards anywhere whatsoever, and there was a little bit of information about how to reactivate one, but there was no information about the fact that you can actually program them using a serial data connection, and you have to look at the particular chip though. If you're lucky enough to be able to read the markings on the chip, you will find ways of reprogramming them to accommodate your own specifications and all that bullshit, you know. So this one is intermittently going off and starting again. That's because the board is on the threshold of turning the power off, because I reactivated it, and we're right on that, right at that point where the board would cut the power completely. So I mean, obviously as soon as one of these cells drops anymore, it's going to go off and leave it off until it's charged. So the board's handy, handy for doing what I want really, as regards thermal monitoring and protecting the cells from total discharge. But it's a little bit erratic as far as turning the power on and off on that threshold, which is a little bit annoying. Yeah, it went off again and it came back on again. Actually, maybe I should have found an LED that stays on all the time. It would have been less irritating. So maybe this information was useful. Sorry about waffling on, I know, but it went up again and came back. And again, it's right on that, right on the threshold of it going off and staying off. kind of useful, I suppose, if you're running the light and you want to have some warning that the battery's about to die on you. At least you're not in total darkness for a while. Okay, enough of that. Thanks for watching.